So, welcome back to this lecture series on pulse width modulation for power electronic converters now. So, we have been looking at various power electronic converters here. So, we started looking at various power electronic converters. We started off with DC to DC converters, and from there we moved on to DC to AC converters. In DC to AC converters, we looked at basically both the voltage source and the current source converters, and in the voltage source we looked at both the 2 level inverter and as well as the so called multi level inverter now. So, today what we will be doing is we are actually supposed to be looking at the applications of voltage source converters. It is basically a kind of an overview of various applications. So, you may not find too much of details here, but there is certain amount of overview that we will get here. And as far as the details of these applications are concerned, you will certainly have, there are other courses where you will have quite a lot of details of these applications might be available now here. Before we when we look at what exactly are these applications of voltage source converters, so some indicative applications are given here. Please this is more indicative and it is kind of not certainly exhaustive now. So, you have voltage source converters, what all you can do with a voltage source converter is kind of a question now. So, one of the application is AC motor drive. You have various induction motors and such kind of you have induction motors which are very rugged now, and what you do is you basically control the induction motor. You try to control the speed of an induction motor by using a inverter now. An inverter is capable of giving you AC voltage, AC of what amplitude, of what frequency, that is kind of programmable. So, you can control, you can get what voltage, what amplitude you want and what frequency you want, and that is what is required in a motor drive, as we will be seeing shortly today. And today in fact, our emphasis will be really on AC motor drives. There are also other applications of a voltage source converter. Everybody knows that a voltage source converter or inverters, they are applied in uninterruptible power supplies. So, what you will have in an uninterruptible power supply is you will have a battery bank. Whenever there is no power supply available in the mains, no power supply is available from the utility, what you do is to invert this battery power and feed your AC loads. So, you use an inverter there now, and this battery itself is charged from the mains whenever power supply is available. That is what typically happens in an uninterruptible power supply, right. Then you also have the so called active rectifiers or front end converters now. So, what do we mean by this active rectifiers? We will look at this in detail in the next lecture. However, we will just look at a few things. What do you mean by a rectifier? Well, a rectifier is that it converts AC into DC, as we know. And what we mean by rectifier, active rectifier, we typically may have diode bridge rectifier, and these diode bridge rectifiers, they are actually non-linear elements. I mean, they draw non-sinusoidal current, right, of pulsating current from the AC mains. Typically, these diode bridge rectifiers will have a capacitance on the DC output, and they draw pulsed current, and which is not sinusoidal at all now. So, the current waveform is not sinusoidal, and also the power factor is very poor. So, what we try doing is we try making use of voltage source converters to perform this rectification, to perform this AC to DC conversion, and those are what are actually called as active rectifiers. In this, you can actually achieve a high power factor, and you can draw almost near sinusoidal currents from the mains. So, these are necessary things that you want now. These active rectifiers are sometimes also called front end converters, because an AC motor drive is basically an inverter feeding an induction motor. So, now that inverter requires a DC supply, and that DC supply is provided by such an active rectifier, and therefore, it is also called a front end converter at times now. Then you have the other application, what I have called as a reactive current compensation. Many a times reactive power is being drawn by many of our loads now, and that is not very good. I mean, the utility wants us typically to maintain the power factor better than some level like 0.8 or something like that, and also there are some tariffs. If you go lower than that, you may have to pay penalty, etc. now. So, there is certain amount of reactive power may have to be injected into the utility at times, and because of the loads I mean basically lagging loads which are already connected to the grid now. So, you need what is called as a reactive current compensation. Actually, a voltage source converter can be used for this reactive current compensation also. Quite often it is called a static compensator, which is abbreviated by this name STATCOM as given here now. This is yet another application of this. So, in case of an active rectifier, what you do is you draw near sinusoidal current from the grid almost at unity power factor or very close to unity power factor. In case of reactive current compensation, what you do is you once again draw near sinusoidal current from the mains, but at a power factor which is kind of close to 0 leading. So, that is what we try doing here now. So, that there is certain amount of power is reactive power is supplied into the mains, correct. Then like it is not only reactive current, this may be reactive current, lot of reactive current is being drawn by various other loads in the plant, and we are using a converter to supply a part of the reactive power. Now, we may also have loads which are actually drawing harmonic currents. The diode bridge rectifier itself is such a load. So, it draws quite a lot of harmonic currents now, and these harmonic currents have to be compensated for. What you can do is you can use voltage source converters to provide such harmonic currents to these nonlinear loads. So, that the nonlinear loads such as a diode bridge do not draw the non-sinusoidal parts or the harmonic components from the mains. So, if you have a nonlinear load draws non-sinusoidal current, which has a fundamental component, which is a sinusoidal component at the line frequency and also harmonic component. So, the fundamental component can be drawn from the mains, but the harmonic components of that can be supplied by another voltage source converter, which is what is called as harmonic current compensation. Again, we will look at this in detail in our next lecture now. This is also called active power filtering. So, these are the various applications of voltage source converters, but as I told you a while back, our focus today will be on AC motor drives, and even in AC motor drives, before we get on to AC motor drives, we will have a quick recap and basically review whatever we did in terms of converters in the previous classes, because that is now quite necessary, right. So, let us take a quick look at what we have been doing, what we did in the last lecture. So, this is basically a 3-phase voltage source inverter, which has been shown in terms of single pole double throw switches. You have 3 single pole double throw switches here, and these are the load terminals R, Y and B, and DC power is fed from here now. So, DC current can flow through this now. In this case, there is a DC to AC conversion, and current can also flow in the opposite direction. If it is also possible that current can flow in the opposite direction, in which case it means that the power is flowing from the AC side to the DC side. If it is flowing from the AC side to the DC side, the power factor here between the voltage and current will be greater than 90 degrees, or will be closer to 180 degrees, so to say, that power can flow. And so, it is really a bidirectional power flow converter, and the actual switches are realized like this now. So, to restate whatever I said, this is the pole of a single pole double throw switch. At this pole, we can apply either this potential, which is plus 0.5 VDC or minus 0.5 VDC, by turning on either the top device or the bottom device, but not both. We can apply this potential either plus 0.5 VDC or minus 0.5 VDC irrespective of the direction of the current. The current can be flowing in this direction or it can be flowing in the opposite direction. Irrespective of the direction of the current flow, we can apply this voltage level now, right. So, depending on the direction of the current and depending on, let us say, the top device is on, if the current is as indicated by this arrow mark, then current may flow in this direction. If the current is really in the opposite direction, then the current will flow through the diode now. So, these are bidirectional current carrying switches as we saw now. So, what you can really have is between R, Y and B is actually the 3-phase load connected, and we presume that the load is inductive, right. Okay. Now, this is, we looked at a 2-level and a 3-level voltage source inverter. In case of a 2-level voltage source inverter, both the inverters you have the same 3-phase load connected, In case of a 2-level inverter, you have only 2 poles, one of them connected to the positive DC bus and the other is connected to the negative DC bus. Whereas, if you look at the 3-level voltage source inverter, you have 3 poles, one of them is connected to the positive terminal, other one is connected to the DC bus midpoint, and the third is connected to the negative DC bus. So, in addition to 2 of these, one connected to the positive and one connected to the negative, you have a third one or the middle one, which is connected to the DC bus midpoint, and that is why we call this as a 3-level voltage source inverter. here if you take a 2 levels voltage source inverter, VRO can be only plus VDC by 2 or minus VDC by 2 as I mentioned the other day. If you take VRO here, it can be either plus VDC by 2 minus VDC by 2 or it can also be 0 in a 3 level inverter. There are 2 different voltage levels here and there are 3 different voltage levels in a 3 level inverter, hence you get the name 3 level voltage source inverter now. So, the realization of a 3 level voltage source inverter also we saw. So, it is a single pole triple throw switch now. So, either the top 2 devices are on and the bottom 2 are off. So, in that case when the top 2 are on, this pole is connected to the top throw, or the positive DC bus now. Again you may have a situation where the middle 2 are turned on, S2 and S3 are turned on, and that means S1 and S4 are turned off. These S1 and S4 the extreme switches are turned off. In that case the same pole is connected to the midpoint here, and the direction of current depends on, if this is the direction of current, then you will have current flowing through the diode and the transistor. If the direction of current is different, let us say it is in the opposite direction as shown by the other colored ink, then it can actually flow in this direction through this transistor and through this diode back here, right. So, you can also think of I mean there is also the other state where the pole is connected to the bottom throw, S3 and S4 are on and S1 and S2 are off. So, now what we have here is I mean this was the same mistake as in the last slide, this should be off here, right. So, these are S1 and S2 are off now. So, you can connect the pole to either of the 3 voltage levels. This is the exact realization of a 3 level voltage source inverter, and the pole can be connected to the DC bus neutral, hence it is also called neutral point clamped inverter or NPC inverter. You use diodes to do this connection, therefore, it is also called diode clamp inverter as we mentioned the other day. Now, these switches S1 and S3 act in a complementary fashion and S2 and S4 act in a complementary fashion now. So, this is how you what we saw earlier was a single leg, now you have 2 legs here, and these 2 legs you can have a single phase load connected between these 2 terminals, and this is your DC bus voltage being fed here. Now. So, this is the other alternative that we looked at is a flying capacitor converter now. So, you use a capacitor which is charged to 0.5 VDC just like other capacitors, and you can connect this in series or in parallel, I mean in series and with one polarity or in series with another polarity. For example, if S1 is closed, then this gets connected in series with these capacitors in a particular polarity, or alternate like S1 can be closed, that is one possibility. So, then the other possibility for example is S2 is closed and S1 is open. In such a scenario, again this is connected in series, but the polarity of this is reversed now. So, in this case if you have connected here, you will have this O is basically equal to you get this potential at O for if let us say the top is turned on, So, this is plus minus and you have plus and minus, and this is where you get the potential of O. So, that is I should make it red color, yeah. So, this is where you get O now, whereas if the connection is as shown by the green ink. So, this S2 is closed and S1 is open, and in this case this point is equal to potential O. So, this is how you get this, and you have a single pole triple throw switch here, and all these switches have to be capable of conducting in both the directions, and you have this was the realization that we saw now. Basically, with all these what we would aim at doing is to realize certain average voltage, that is what we will be looking at shortly from now on. So, this is another one leg of a what is called as a multi-cell inverter now. If you need different voltage levels between A and N, what you try doing here is you use one simple single phase bridge. So, this is a single phase bridge, you can connect 2 of them and you can make a connection like this, and so between these 2 points you can have various voltage levels. It can be VDC, it can be 0.5 VDC, it can be 0 or it can be minus 0.5 VDC or it can be minus VDC. So, the different voltage levels are possible here, and this is where you can connect one of the phases of the load across these two terminals now. This is again one leg of a multi-cell inverter now. So, these are various topologies for realizing what are called as multi-level, what is really a multi-level inverter. So, if you just look at what we are going to be primarily concerned is, this is about a DC to DC converter. What you have is a DC to DC buck converter. In this you have a single pole double throw switch, and there is certain potential at the pole now. What is that potential at the pole? That potential at the pole is essentially the voltage, output voltage. And how is it related to the input voltage? It is related to the input voltage as certain duty ratio times V in. The duty ratio meaning, like you connect P to T1 for some time and P to T2 for some other time. So, you keep on doing it in a cyclic periodic fashion. So, the time for which you connected to T1 divided by the total switching time is the duty ratio as we defined now. So, you get this as a duty ratio times V in now. So, you get some potential at the pole which is lower than V in. So, what you are doing is this is the pole and there are two throws now, and you are controlling the potential at this pole. In case of a 2-level voltage source inverter, this is a 2-level voltage source inverter, as you can very clearly recognize. This is a 2-level voltage source inverter. So, now let us take the point of reference as this midpoint O. Now, if you want to mean R, what you are going to do is you look at this potential VRO. At any instant it can be either plus 0.5 VDC, this potential is VDC by 2 and this is another VDC by 2. So, the potential at R at any instant can be either plus VDC by 2 or minus VDC by 2. And what you will do is, you will do an averaging, you will connect it to the top throw for some time and the bottom throw for some time. So, the average potential at R will be somewhere between plus VDC by 2 and minus VDC by 2. So, the same story about Y and the same story about B. So, if you look at a 3-level inverter, once again it has 3 switches, but in a 2-level case it is all single pole double throw, here it is a single pole triple throw switch. So, this is a 3-level voltage source inverter. You have single pole triple throw switches here. Once again what you do is, as at this potential R, potential at R with respect to O can be either plus VDC by 2 minus VDC by 2 or 0. So, and what you can realize is, you can realize any potential that is anywhere between plus VDC by 2 and minus VDC by 2 in an average sense. So, that is what you can do now. So, let us look at more of this in the following slide. What you want to do in a steady state, at steady state in a DC to DC buck converter is to produce certain output voltage now. This output voltage is nothing but the DC voltage here. So, if I call this potential at Vp, and this Vp has certain average value, this Vp is like plus V in some time and it is equal to 0 some other time. So, it has certain average value, this average value I am calling it as Vp average. Now, what is this Vp average equal to? This Vp average is actually equal to the DC output voltage that we want. This is equal to V out and this is equal to D times V in, as I just said a while back. So, the pole voltage cycle by cycle is controlled in such a fashion that the average voltage is the same, the average voltage does not vary, whereas if you move to an inverter, that is going to change now. Here also you have this pole voltage, pole at R. Now, we are measuring it with respect to the midpoint O, VRO, and we are looking at this VRO average. What we are looking at is the potential V at the pole R measured with respect to O and the average value, this is the instantaneous, and we are trying to average this over a switching cycle, and what we call it is VRO average now. So, this VRO average can be anywhere between plus VDC by 2 and minus VDC by 2, because this has a potential VDC by 2, this also has a potential VDC by 2. VRO can be, the instantaneous value is either plus VDC by 2 or minus VDC by 2, and it can be averaged, that is you can apply plus VDC by 2 for some time and minus VDC by 2 for some other time, and therefore, it there is a kind of a time averaging that you are doing now. Due to this time averaging, you can realize any value that is anywhere between plus VDC by 2 and minus VDC by 2. And what you do here is, this average voltage is varied now in a sinusoidal fashion. Since you want sinusoidal output voltages, one simple thing for you to do is to vary the average pole voltage in a sinusoidal fashion as I have shown here. Now, for example, so small switching cycle and this is the average voltage that I am applying. Now, in the next switching cycle I am applying a slightly higher voltage and it goes on increasing as I have shown now, and it takes a sinusoidal nature. So, this is what you can end up doing now. So, here there is a question now, if VRO average is modulated like that, how should VYO average be modulated? In a similar fashion, in a similar sinusoidal fashion, but phase shifted by 120 degrees. Again, how should B phase be modulated? In a similar sinusoidal fashion, but phase shifted by 240 degrees from R phase. So, this way you can get 3 phase sinusoidal outputs now. So, you look at this voltage now, let me say this value from 0, this is the average voltage now. This average voltage can be anywhere between minus VDC by 2 to VRO average can be anywhere between minus VDC by 2 and plus VDC by 2. So, now if I look at this, what is the highest voltage that I can get here? Let me use red ink here. So, this is what is the highest value that I can have? The highest value that I can have is VDC by 2. This is the highest possible value. Now, I can, that is what I am trying to say is the pole voltage is controlled in such a fashion that this average, its average value averaged over a switching cycle varies in a sinusoidal fashion, and you can control it in such a fashion that the peak value of the sinusoid is VDC by 2. So, this is the highest amplitude of average sinusoid that you can produce. VRO average, if you look at it and if you want to modulate VRO average as a sinusoid, the peak value of the sine, the amplitude of the sine cannot exceed VDC by 2. So, this is the highest amount of voltage that this inverter can produce with such a sinusoidal modulation. It is not necessary that VRO has to be modulated in a sinusoidal fashion. For example, it can also be as a sinusoid with some triplet harmonics added to it, etc., which we will see in a few classes later, a few lectures later. Now, but you take it as sinusoid, this is a limit on this now. If you really want very high voltage, what you need to do is you need to go in for a square wave operation, but if you are looking at sinusoidal modulation, this is the highest value of VDC by 2 that you can get now. You can get any value, let me call this as M VDC by 2, where M is anywhere between 0 and 1. M can be anywhere between 0 and 1. So, you can with the voltage source inverter with a DC bus voltage VDC and the average pole voltage is modulated in a sinusoidal fashion, it is possible for you to get a peak phase voltage up to VDC by 2, some M times VDC by 2, where M is a fraction anywhere between 0 and 1. So, it is possible for you to control the amplitude. It is also possible for you to control the frequency now. It is possible to control the frequency also. So, the rate at which the average voltage varies, it can be controlled now. So, both the voltage and frequency can be controlled here now. If you look at a 3 level inverter, what is the story there? Again here also, if you look at the average pole voltage, unlike in a DC to DC converter, the average pole voltage is maintained constant at steady state. In a 2 level inverter, like it is maintained constant, in a buck converter it is maintained constant here. In a 2 level inverter, the average pole voltage is now varied in a sinusoidal fashion, right. Please realize that the average voltage is never greater than plus VDC by 2 or minus VDC by 2. So, this is also what is called as a buck derived topology. Now, if you say, if you take this here again the average pole voltage can be only anywhere between plus VDC by 2 and minus VDC by 2. So, here also you can vary it in a similar sinusoidal fashion now. So, this is in this sense it is similar now, that is once again you can modulate, and what is the peak value that you can get here? The peak value that you can get here if you are modulating it in this fashion is like VDC by 2. This is something that you can get here. So, you can control this to any value which is less than VDC by 2. So, if both are sinusoidally modulated, in a 2 level inverter also you can modulate it sinusoidally, in a 3 level inverter also you can modulate the average pole voltage in a sinusoidal fashion. What is really the difference between the two? The way the average voltage is realized, the way the average pole voltage is realized is different between a 2 level inverter and a 3 level inverter. In a 2 level inverter, there are only 2 voltage levels that can be applied at the pole. One is plus 0.5 VDC and the other one is minus 0.5 VDC. Now, if you need an average voltage as indicated here, what you do is, this is the average voltage you have indicated here in these dashed lines. What you do is, you connect the pole to the top throw for a long period of for some time and connect it to the bottom throw, so that it is equal to minus 0.5 VDC for a short duration of time. So, the result is you get an average value, and the average value is what is given by VRO average now. In this case, this VRO average is something like 0.25 VDC. Now, let us say you want the same 0.25 VDC as an average applied here in a 3 level inverter. What you can do is, you can connect the pole to the top throw, that is plus 0.5 VDC for certain amount of time and to 0 for the remaining amount of time. So, this is for 50% of the time, this is another 50% of the time. So, you are once again getting the same average value, this average value is same in the two cases, but what is different? The instantaneous applied voltages are different. How are they different? In here it is plus 0.5 VDC and minus 0.5 VDC in a 2 level case, whereas in a 3 level case it is plus 0.5 VDC and 0. So, the worst case error between the applied voltage, where what is the worst case error here? In this case, the worst case error is here. This is the worst case error between the applied voltage and the desired voltage, which is the average voltage, whereas in the case of a 2 level inverter it is much lower. This is the worst case variation, and this is also same as that. So, you can see that the worst case error between the two is reduced, that is the instantaneous error voltages are reduced. This is what leads to a better waveform quality. Your harmonic distortion is going to be substantially lower because of this. So, that is why a 3 level inverter is said to give a better waveform quality than a 2 level inverter. This is something we saw in the previous class now. So, going back to this, either you are talking of a 2 level inverter or any multi level inverter, it is possible for you to modulate the pole voltage in a sinusoidal fashion, and we are going to modulate the pole voltage in a sinusoidal fashion now, right. So, if this is VRO average, let us take a look at how are the other average pole voltages now. This is VRO average. As I mentioned here, this VRO average can have a maximum value equal to VDC by 2, that is its peak value can be equal to VDC by 2, or it can be anything like M VDC by 2, where M is anywhere between 0 and 1. This is what you can have now. So, if your VRO average is controlled here, then your VIO average is as indicated here is 120 degree phase shifted, and we are taking they are revolving like this, and VBO average is another phase shifted by yet another 120 degrees now. So, this is how, if R is modulated in a sinusoidal fashion, Y and B are also modulated in sinusoidal fashions. They also have the same amplitude, there is only a phase difference now, all of this are at the same frequency, right. So, if this is VR, how about the line to line voltages? So, this is what we have at VRO average. VRO average is a sinusoidal quantity, that is why we are representing it as using phasor. So, VRO average, VYO average and VBO average are all phasors, are represented as phasors because they are sinusoidal quantities. How about VRY average? VRY average is nothing but VRO average minus VYO average. So, this is VRO average and this is VY minus VYO average. So, VRO minus VYO average gives you this VRY average. You can see that this is going to be root 3 times of VRO average now. If you VRO average is something like 200 volts, that will be 200 into root 3. So, similarly, VYB average is equal to VYO average minus VBO average. If VBO is projected this way, this is VBO average now. So, VYO minus VBO average, this is minus VBO. VYO minus VBO gives you VYB. The same way, VBR is equal to VBO minus VRO. VBO minus VRO average. This will give you this thing. So, that this is how you have your 3 phase line to line voltages, 3 phase average pole voltages and the 3 phase line to line voltages now, and the amplitudes are controllable. The amplitudes are controllable, right, that M it can be anywhere between 0 and 1. So, it is controllable up to VDC by 2, right. So, you can also control the frequency. So, you can control the amplitude and you can control the frequency, and this is what helps us in controlling an induction motor as we will see shortly now. So, let us look at now an induction motor now. So, this is the torque speed characteristic of an induction motor when some particular voltage V has been applied. The stator voltage is some particular V, let us call it. So, for this value of V, this is how you get here. You can easily obtain this from the steady state per phase equivalent circuit of the induction motor also now. So, the torque, this is what is called as the starting torque, and it goes on. You can, as you know, that the induction motor is self starting, it has certain amount of starting torque, right. There are courses on electric machines available on NPTEL which describe in detail about the operation of an induction motor, right. So, you have a characteristic like this, and this part of the characteristic is called unstable and this part of the characteristic is called stable. Why is it? So, how does the operating point is, how is this is the torque speed characteristic of an induction motor. Now, where exactly will it operate? It can operate on any point on this curve. How is that point chosen? It can be here, it can be here, anywhere. How is that chosen? That is chosen by the intersection of the load. If let us say we have a load whose characteristic is like this. This is the load, let us say the load has such a flat torque speed characteristic. So, this will be the point of operation, and this point of operation is supposed to be stable. Why is it stable? Let us say there is a small disturbance. Because of the small disturbance, this point moves here. So, if this point is moved here, what happens is the torque is now lowered, the torque is now lower than what it was. So, the machine will naturally decelerate and it will go back to the origin. So, you can see from this operating point, you can look at any kind of disturbance you can look at either in torque or in speed, you will see that the operating point will return to this point. So, let us call this point P. So, for any disturbance it will tend to come back to this operating point, and therefore, you call this operating point a stable operating point, and the set of all operating points on this region are supposed to be stable like this. So, you call that as the stable region of the torque speed characteristic of induction motor now. So, why is this side called unstable? The same way, if you have a load torque characteristic like here, and now let us consider a point Q. From Q, if let us say if the motor somehow shifts and goes to this operating point, what has happened now? The torque has increased now, the speed is already little higher and the torque is higher. So, the torque produced by the motor is higher than the torque demanded by the load, and therefore, it goes on accelerating. Therefore, it will move away from this particular operating point. So, if you at P any disturbance you consider will you will see that there is a tendency of the motor load system to come back to this operating point, whereas at the operating point Q, in case of any disturbance, it will run away from that operating point, it will not come back to that operating point, and therefore, you call this as an unstable operating point and this entire region as an unstable operating region. Now, there could be a question, can I operate it in the unstable region? Is it possible at all to operate it in the unstable region? Yes, you can operate it. For example, let us say you have a load torque characteristic like this. You observe the relative slopes. What I mean by relative slope? At this point Q, the torque speed characteristic of the motor has a particular slope, and the green line indicates a particular slope of the load, and the red line indicates yet another slope, right, of the load torque speed characteristic. If the load were having a torque speed characteristic as indicated by the red ink rather than as indicated by the green ink, the situation is different now. Let us say from this operating point Q, it once again goes back here. So, what happens? It is now producing a slightly higher amount of torque, but at that speed the torque demanded by the load is still higher, and therefore, there is a decelerating effect and the motor load will come back to this same point Q. So, it is possible to operate it in the so called unstable region by having a different kind of torque speed characteristic as I have shown here now, but we generally do not do that, because at this point if you look at, there is the slip of the machine. So, if you look at, this is the slip here, and in this case this is the slip here at the point Q now. So, what is the slip now? There is this point is the synchronous speed. This point Ns is what is called as the synchronous speed of the machine, that is, it is the speed of the synchronously revolving magnetic field that is rotating inside the machine because of the 3 phase voltages applied on the 3 phase stator winding. Now, if you consider this operating point P, let us call this speed as n. So, slip S is basically ns minus nr by, or let us just ns minus nr by n. Let me remove that using, it is ns minus n divided by ns. So, this is the slip now. So, the rotor side resistance in a motor is basically, you would have seen that in a equivalent circuit it is R by S. Now, in this case the slip is very small and therefore, R by S is substantially high. If you take the next case, this operating point Q, the slip corresponding to the operating point Q, let me call this as n subscript Q, just to distinguish it from this n. So, NQ minus NS is now very high and therefore, the slip is very high. If the slip is very high, R by S is actually very low. So, normally in induction motors will operate with a slip of just a few percent points. So, R by S will be much higher than RR. If S becomes higher and higher, RR by S comes lower, and therefore, your slip in the rotor resistance is high. What I am trying to say is, it is going to draw very high current, prohibitively high amount of current. So, it may not be possible for you to operate in this operating point Q in a sustained fashion, whereas this operating point P it is possible for you to operate for a reasonably long period of time. So, this is our understanding about the torque speed characteristic. Here what we are trying to do is, what we have done is, we have considered a particular voltage which is this V, as I have indicated here. This is the stator voltage now. We have also considered a particular value of frequency, say something like Fs is equal to 50 hertz. This is the stator frequency now. So, you know that 120 times Fs by P is what is your synchronous speed now. So, that is your synchronous speed now. So, this is for a particular stator voltage and a particular stator frequency. So, we should move on to what happens if we vary one of them. Let us first vary the stator applied voltage. So, now this is the torque speed characteristic with variable voltage. We are still looking at the same torque versus speed, but the voltage is now varied now. This can be some voltage V1, this is some voltage V2, V3, some voltage V2, and the voltage is decreasing in this direction. Voltage is decreasing in this direction. As if you reduce the voltage, the peak value of the torque speed characteristic really comes down. You might already know this very well. If you do not know, you can verify this very easily. You can also verify it from the equivalent circuit of the induction motor now. So, it comes down and V3 comes down. So, it goes lower and lower now. Okay. So, this is also possible. This is where the characteristic changes now. So, if you consider a particular torque speed characteristic, let us say you have a load torque like this. This is your load torque characteristic. When you have applied a voltage V1, you have the motor operating at this point like this. When you reduce the voltage, it will come down to another point like this. So, it is possible for you to vary the speed of the motor over a small range by going in for such kind of voltage control, but it is restricted over a small range. It is restricted only within this so called stable operating region here, and this is ideally suited, as you might know, for characteristics like here. You may have certain characteristics like in pump or such kind of loads, which will have a characteristic going up like this. So, which is typically used in such drives, pumps, etc. They may have a kind of a parabolic relationship between torque and speed, and so sometimes it is used there in this situation here. But what we want to now see is, this is the effect of varying the stator voltage on the torque speed characteristic now. So, if you instead of applying the rated voltage, let us say about 400 volts, if you apply 200 volts or 300 volts, what happens is, you find that the torque speed characteristic changes in this kind of a fashion, that the peak torque essentially comes down, right. So, now let us look at the next scenario, where both the torques, both the voltage is varied and the frequency is also varied. In the previous case, we kept the frequency unchanged. The frequency unchanged meaning the synchronous speed was unchanged down. So, now you are changing the frequency. This is some frequency f1, this is some other frequency f2, this is some frequency f3. If your stator frequency is equal to some f1, then you will have a corresponding synchronous speed ns1. This will be like the same 120 f by p, and F is now changed from 1, 2, 3 etcetera, and we are typically considering a 4 pole machine, let us say. So, for a 4 pole machine, for 50 hertz would mean 1500 rpm, and if it is 50 hertz is changed to 40 hertz, then this 1500 rpm will get reduced to NS2. NS2 will be something like 1200 rpm now, and F3 if it is 30 hertz, there will be a corresponding synchronous speed NS3, and this will be something like 900 rpm now. So, what happens is the synchronous speed changes if you do that now, and if you do it in such a fashion that the voltage to the frequency ratio is kept constant. This means effectively that the torque, I mean the flux is maintained at the constant value. So, therefore, the peak torque is not never getting affected. Earlier if you see that the peak torque was getting affected. Why? Because the frequency was held the same, but the voltage was reduced. You have V1 by F. Now, V1 by F is actually greater than V2 by F. Therefore, when you apply V2 which is lower than V1, the peak torque comes lower. This is again greater than V3 by F, and therefore, you see that the peak torque goes on changing with the V alone. Now, what we are trying to do is we are varying both V by and F, and that ensures that the peak torque is fairly constant, and the effect is basically that you see that the characteristic itself is getting shifted. What you see is that the torque speed characteristic is kind of getting shifted everywhere. So, what? Now, let us say I have a load whose torque speed characteristic is like this. Let me use a different color. Okay. So, let me use this green color. Let us say this is the torque speed characteristic of the load. So, if I am applying a frequency F1 and a corresponding voltage V1, let us say, let me call this corresponding voltage is V1, then I operate at this point. If I apply a frequency F2 and a corresponding voltage V2 such that V by F is constant and it is equal to its rated value, now I can operate here at this point. Let me just change the color, let me say I can operate here now. So, this is when I have V2. Now, let us say I have yet another operating point, this is F3 and V3. So, here the same load it can operate at this point. So, what you can do is you are able to control the speed. The speed was earlier here and that speed got reduced to so much, and then this speed is getting reduced to so much now. What are you doing essentially here? Earlier in this case like a variable voltage, what happens is it is an induction motor. In an induction motor you are applying, it has a 3-phase stator winding and you are applying a 3-phase voltage now, and this 3-phase voltage produces a revolving magnetic field. It produces a revolving magnetic field inside. So, like this there is something, it is a magnetic field that revolves now. At what speed does it revolve? It revolves at a speed which is directly proportional to the frequency now. So, here what you are trying to do is you are not changing this frequency, but you are trying to change the slip. By changing the slip you are trying to vary. Here what you are trying to do is you similarly have a revolving magnetic field inside. What you have is a revolving magnetic field. You want to control the speed of the induction motor. What can you do? One of the easiest things for you to do is to reduce the speed of this revolving magnetic field. Let me call this as omega s or Fs. If I can just reduce the speed now. It is an induction motor which will typically run at 1500 rpm, something close to 1500 rpm. Now, I want it to run at a speed close to 750 rpm. What should I do? I must reduce this speed of this revolving magnetic field by roughly by 50%. How can I do that? I can very easily do that by reducing the frequency to 50% of its rated value. Instead of applying 50 hertz, I can apply 25 hertz now. So, speed control is achieved here by essentially by controlling the speed of this revolving magnetic field, that is by controlling the stator frequency. But for this you have to make sure that the magnetic field is, the strength of the magnetic field is constant, and that is given by this ratio V by F, that is given by this ratio V by F, and you maintain this V by F at a constant value equal to its rated value. Therefore, you can maintain the flux at more or less equal to the peak flux now. Of course, here we are making an assumption that the resistance drop is negligible. Basically, V equals IR plus d psi by dt, and we are neglecting the IR term here. So, the resistive drops are negligible, you do that. When you go to lower and lower speeds, the resistive drops might not be negligible, and therefore, if you reduce frequency much lower, you may find that your peak torque is really little lower than that. At here you may find the peak torque to be kind of lower than what you get here. So, what you do typically at lower frequencies is you boost up V, you do not maintain V by F at the rated value, you keep V at, I mean you make it a little higher than what it should be. So, this is what you do to take care of that effect now. So, what is it that you are able to do now? You are able to control, let us say this is the rated torque, let us say this is somewhere the rated torque now, you are able to operate your machine over the entire range now, you are able to operate your machine the entire range. The load torque is whatever it is, but you are able to change the torque speed characteristic of an induction motor, you are just able to pull and push it, it is like drag and drop that you might do with your mouse, something similar to that you are able to do here by changing its voltage and frequency. And now the point of intersection is different now. If it is a point was P, excuse me, this point is Q and this point is R. The same torque speed characteristic, it can either operate at this so called point P, Q or R. How do you do that? By changing the characteristic. V1 F1 makes it operate at point P, V2 F2 makes it operate at Q3, and if the applied voltage is V3 and the frequency is F3, you get it to operate at R. So, this also gives you a fairly simple way of getting the induction motor started. How do you get an induction motor started? As you always know that the starting currents are very high. If a direct online start, you may get currents roughly some 5-6 times the rated current as your starting current, but that is only for a short duration of time and the motor is designed to stand that. But many times you want a smooth starting. Why? Because your inverter, your motors, if it is going to be fed from an inverter, the motor can take a high starting current, but the inverter might not be able to take a high starting current. That is one reason why you have to limit your starting current to as low as possible now. So, how do you do that now? So, let us say you want to keep it very low. So, what you can do is you shift it to a point, let me use a different color that I have probably not used till now. What I can try doing is I can shift this like this, I can shift the characteristic like this, such that this is my rated slip frequency and I bring it to here. So, in this case what I am trying to do is I am trying to apply something as F minimum I call, this is the F minimum, and this produces a very small synchronous speed, and this synchronous speed and here the rotor speed is 0. So, here the slip is small and the slip is still comparable to that of the rated slip. As long as this slip is not very high, let us call this as starting slip, I will call this as slip at starting, this should be equal to whatever is my NS minimum. Let me do my slip at start, is going to be this F minimum corresponds to certain NS minimum, this is NS minimum, and what is N? N is now 0 and I can come up with whatever is my NS minimum. So, this excuse me. So, here the slip as such is high. If you look at the slip frequency here, the difference is, excuse me, so you look at this, let us say this is the rated operating condition, and this is your synchronous speed now. So, this is the difference between what you would call as the rotor speed and the synchronous speed. At start, if you keep your speed such that the synchronous speed at start and the 0, I mean the rotor speed is 0. If you keep the difference between the two, or just the synchronous speed at start to be lower than or comparable to that of this difference, that is the rated synchronous speed and the rated speed, then you are okay. You are going to have a slip frequency which is much small and your machine is not going to see a large amount of current. So, what we are basically trying to do is we are trying to, if you want a smooth start, we come to this waveform as I have indicated here. We come to this kind of a torque speed characteristic. So, the starting torque is now fairly high and that could be close to the rated torque, and once the machine picks up speed you can gradually go on increasing the frequency, you gradually go on increasing the frequency, so that the torque speed characteristic also keeps shifting to the right and you can eventually move to wherever you want to move towards the end now. So, thus you are able to control now. So, what are you doing now? You are controlling the speed now. It is not an induction motor, an induction motor is now an induction motor drive. Why? Because it is a controlled induction motor. What is being controlled? Its amplitude and frequency of the applied voltage are being controlled using a voltage source inverter. So, if you when you want a voltage source inverter for induction motor drives, so why do you want? Because an inverter can produce 3-phase AC voltage and of variable amplitude and variable frequency. Of course, there is an upper limit on the amplitude up to which you can do that, and again there is a variable frequency, and this frequency has to be also substantially lower than the switching frequency of the inverter now. So, since you are capable of doing this, your an inverter can be used for speed control of induction motor, and such things are called as adjustable speed drives or variable speed drives now. The most commonly used ones are open loop constant VBF drive, that is what we discussed till some time back. So, we discussed VBF drive. So, we change the voltage, we change the frequency, to depending on the speed at which we want to operate, and the voltage is always maintained proportional to the frequency. So, that the flux is more or less maintained constant now. Here you can also operate it at slightly higher speeds if you want, but beyond the rated voltage you can't apply a voltage beyond the rated voltage because of insulation, that there is a limit there. So, what you need to do is, if you go to frequencies higher than this, you have to apply it at a lower voltage. So, VBF ratio reduces. So, that is actually called flux weakening now. So, this course is not so much on the extensive control of induction motor. There are courses on motor drives again on NPTEL, which will give you a thorough understanding of these various aspects of controlling this now, right. So, it is also possible that you can do it in the there is something called a super synchronous operation, and there is braking and such things you can get a detailed idea about other of this induction motor drive operation in other courses in this NPTEL forum now. So, what we have also dealt with is basically is open loop constant VBF drive. This is what we will be dealing with primarily in this course now, but there are also closed loop drives. This open loop VBF drive is okay when you do not need a very good dynamic performance, its steady state performance is alright. When you want to change from one operating point to another operating point, it is going to take considerable length of time. So, for high dynamic performance you will go for closed loop drives. This is for when you require a high dynamic response, very fast dynamic response, you go for closed loop drive. These closed loop drives are various things like vector control and torque control, direct torque control, etc. Now, vector control is also called as field oriented control, etc. What we try doing essentially is, you see that the same it is just a single 3-phase voltage is being applied and 3-phase currents are being drawn. In the case of a DC machine, you have a separate field winding and an armature winding. So, field winding is current is controlled separately and armature current is controlled separately, whereas in the case of an induction motor, both the torque component and the flux producing component of the currents are drawn from the same source. What we try doing is appropriately by modeling, it is possible for us to determine what is the torque producing component and what is the flux producing component. We can control these two in a fairly independent fashion. It is possible for us to change only the torque producing component of the current without changing the flux producing component of the current. That is what in essence is vector control. In a DC motor drive, you can leave the field current unchanged and you can only change the armature voltage and change the armature current. So, you can just change the torque without changing flux. So, similarly, in an induction motor also, it is possible that you do not change the flux producing component of the current and change only the torque producing component of the current. That is what you do in field oriented control or vector control. As I said before, there are other courses available on NPTEL which can give you a very good exposition on vector control of induction motors, and I would ask you to go through such kind of courses to get a good understanding of closed loop things. And direct torque control is yet another variety of closed loop operation of this thing, and various closed loop control for not only for induction motor but other variants. This is what we have been looking at as a squirrel cage motor, for slip ring induction motor and synchronous machine and permanent magnet motors and varied kinds of motors. You have drive operation is possible. All this control of such various drives are dealt with in various other courses now. So, here today we have primarily looked at the voltage source inverter feeding an induction motor, that is what we have looked at. The other applications, as I mentioned before, is an uninterruptible power supply, and again as you are already aware that it is basically it has a battery. You need an inverter which will invert and provide power to AC loads whenever the mains are off. So, it basically has that that is an uninterruptible power supply. About this active rectifier, we just had a brief discussion at the beginning, and in the next lecture we will have a fairly detailed discussion on this active rectifier. So, where rectification is done, DC to AC conversion is done, but a diode, unlike a diode bridge rectifier, an active rectifier draws near sinusoidal currents and draws these currents at a fairly high power factor, something close to unity now. Again, as I mentioned before, a voltage source converter can be used to compensate reactive current. If other loads are drawing a lot of reactive current, you can have a voltage source converter that supplies part of this reactive current or most of this reactive current, and that is what is called as a STATCOM or a static compensator. And once again, if you have non-linear loads which may be drawing harmonic currents, it is possible for you to supply these harmonic currents using a voltage source converter. So, that is what is called as harmonic current compensation or active power filtering. So, these are some applications, namely like active rectifiers and reactive current compensation and harmonic current compensation. These are some issues and applications of voltage source converters which we will discuss in our next lecture. So, I thank you very much for your patience and your interest, and I hope you found this lecture useful, and I look forward to seeing you again in the next lecture. Thank you very much.